Welcome to another video of OptaTube. Okay, I want you to picture this. Imagine waking up on a freezing cold winter morning in Germany, and the year is 2027. The factories are humming to life, steel plants are firing up their giant furnaces, chemical facilities are churning out ammonia, and millions of homes are cranking up the heat as the power grid absorbs yet another massive winter peak. But deep underground, something fundamental has completely changed. You see, the exact same pipelines that once carried natural gas across Europe are now suddenly expected to transport one of the smallest, lightest, and honestly most difficult molecules in existence: hydrogen. Not oil, not coal, not methane. Hydrogen. This isn't just some routine energy transition, guys. We are talking about one of the largest, most complex, and literally unprecedented infrastructure transformations in modern European history. In 2027, well, that's our ticking clock. Following some massive geopolitical shifts and this immense pressure to cut dependence on imported fossil fuels, Germany has basically put its hydrogen economy plans on overdrive. But I really want to emphasize here, this isn't just about casually swapping out a fuel source. No, this is an absolute race against time to replace an entire industrial ecosystem before that winter hits. Energy infrastructure just doesn't update overnight like an app on your phone, right? It takes environmental approvals, construction permits, intense pressure testing, and incredibly complex cross-border agreements. If even one major compressor station gets delayed by just 6 months, downstream industries lose their fuel. Storage facilities get totally unbalanced, and prices absolutely spike. The whole network acts like a highly tensioned chain, and it literally only takes one weak link to snap it. To truly grasp the macro scale we are dealing with here, just look at this number: 9,700 kilometers. Germany is trying to build or convert roughly 9,700 kilometers of high-pressure hydrogen backbone infrastructure. We are talking vast cross-border corridors and absolutely enormous compressor stations. And here is the real kicker. All of this has to happen while industries just keep right on operating. I mean, you can't exactly hit pause on the entire European economy to lay down new pipes, right? Okay, let's dive into this. Section 1. Why hydrogen behaves differently. The molecular hurdle. A lot of people naturally ask, why can't we just pump hydrogen through the existing natural gas pipes? I mean, gas is gas, right? Well, let's shrink down from that massive continental scale and look at the microscopic level. This right here is the core physical problem. Think of methane, that's the main stuff in natural gas, like a bunch of basketballs trapped inside a mesh net. Because they're relatively large and dense, they just bounce off the net and stay safely contained. But hydrogen molecules are insanely small. They have incredibly low density, and they diffuse so fast. So if methane is a basketball, hydrogen is a grain of sand. Try pouring sand into a basketball net and see what happens. It just slips right through. In a real-world pipeline, this means hydrogen easily penetrates tiny seals, welds, and joints that methane would never get through. That's exactly why we can't just reuse the old infrastructure without some serious modifications. Moving on to Section 2, the embrittlement crisis, the hidden threat to steel. Because leaking seals are actually just the tip of the iceberg. Let's zoom in even further to the most dangerous engineering hurdle, which is hiding deep inside the metal itself. It's called hydrogen embrittlement. This is a phenomenon where hydrogen atoms migrate into tiny structural weaknesses in steel, decreasing its ductility and forming microcracks. This is hydrogen's dangerous little secret. Steel might look rock solid to us, but on a microscopic scale, it's full of tiny grain boundaries and structural imperfections. Those tiny grains of sand, the hydrogen atoms, literally migrate into those weak points and rot the giant steel pipes from the inside out. They actually attack the toughness of the metal. And here is how that microscopic damage becomes a real-world nightmare. Pipelines aren't static, they are constantly breathing. They go through pressure cycles. Step 1 is pressure expansion, Step 2 is pressure contraction, and over time, that repetitive stress leads to Step 3, crack propagation. Think about taking a paper clip and bending it back and forth over and over. Eventually, it just snaps, right? Now imagine that exact same process happening inside thousands of kilometers of underground steel under massive pressure. This is exactly why researchers are frantically running accelerated aging experiments and fatigue tests right now, because frankly, nobody wants a surprise rupture in a continental energy system. All right, let's zoom back out to the macro level for Section 3, upgrading pipes and compressors, saving the old infrastructure. So if old steel pipes face these crazy risks, why not just dig them all up and put in brand new hydrogen-safe ones? Simple. The cost. Rebuilding Europe's entire energy grid from scratch would require truly astronomical sums of money. So engineers are desperately searching for a middle path. Now, what's really interesting here is the sheer variety of retrofitting technologies they're stress testing right now. We're looking at things like internal coatings, polymer liners, surface treatments, changing the operational pressures, and rolling out advanced monitoring systems. Imagine literally threading a giant protective polymer sleeve inside an aging steel pipeline. It acts as a barrier so the reactive hydrogen never actually touches the steel. But it also opens up a whole new can of worms. How long do these coatings actually last? What do you do about the thousands of weld joints? And if they fail after a few decades, can we even fix them quickly? And let's say we completely perfect the pipes. We still have to actually push the gas through them. Pipelines are really only half the story. The other half is pressure. Natural gas systems use these massive compressor stations that act like giant mechanical hearts, literally pumping energy across hundreds of kilometers. But because hydrogen is so much less dense, moving the same amount of energy requires vastly more volume and way more power. Suddenly, the old existing compressors become wildly inefficient. The aerodynamics, the mechanics, the rotation speeds, all of it has to change. It essentially turns these giant mechanical hearts into massive energy sinks, which leaves us asking a rather uncomfortable question. How much energy are we spending simply to move energy? Let's shift our focus geographically. Section 4. Connecting Europe's industrial heartland, the logistic chain. Because infrastructure doesn't exist in a vacuum, right? Even if we completely solve the physics of embrittlement and we fix the compressors, this gas still has to physically cross a really complex international map. We're dealing with a stark geographic divide between supply and demand. Up in Northern Europe, you have the production hub, taking advantage of all that massive offshore wind and giant electrolyzer projects. But then, way down in the Ruhr area of Germany, you have the consumption hub. That's where you find these incredibly energy-hungry steel plants and chemical manufacturers. So getting molecules from point A to point B requires seamless, intense coordination across borders, with places like Norway, the Netherlands, and Denmark. You've got multiple countries, totally different regulations, and various grid operators. Literally, one delayed pipeline segment in the north can starve the entire industrial heartland down in the south. So the crucial point is this. Section 5, Economics of the Mega Project, the financial reality check. Engineering and geography, completely meaningless if the economics don't actually work out. Let's look at the scaling reality here. We're talking about jaw-dropping investments. It's one thing to run a highly successful, promising little pilot project in a controlled lab or a single small town. But scaling that exact same process up to a continental level, that is an entirely different beast. A tiny mechanical inefficiency in a compressor suddenly balloons into a billion-euro problem. A slight cost increase for a protective pipe coating could actually threaten Germany's industrial competitiveness on the global stage. And at the end of the day, all those costs inevitably cascade down, which means incredibly volatile energy prices for everyday consumers and heavy industry alike. Which brings us to our final verdict, the million-dollar question. Can Europe actually pull this off by winter 2027? Technically speaking, partially. I mean, the science is absolutely there. The retrofitting tech exists. But as we all know, just because something is feasible doesn't mean it's ready. Doing this kind of massive multi-country retrofit under such a brutal deadline makes this one of the biggest, most volatile engineering stress tests in modern history. If they nail it, Europe basically lays the foundation for a brand new economy. But if they stumble, winter 2027 is going to expose just how dangerously difficult it is to actually replace fossil fuel infrastructure. The future of energy isn't just arriving, it's literally being built right under our feet as we speak. But the ultimate question remains, will this massive 2027 gamble trigger a new industrial golden age, or will it leave the continent freezing in the dark? Well, if you are interested in energy market and power system modeling and updates and insights about global energy market, let's follow OptaTube YouTube channel. Stay curious, stay focused, and I'll catch you in the next explainer.